Hi guys, let's do 0, 1 matrix. So we're given an m by n binary matrix called mat, and they want us to return the distance of the nearest 0 for each cell, and the distance between two cells sharing a common edge is 1. So in example 1, we're given this matrix, and they want us to return this output, which basically how this works. Sorry, let me get this set up for a second. Okay, so basically how this works is all of these zeros stay at 0 in the result because the nearest 0 to itself is going to be itself, which is 0 steps away. And this 1 will be a 1 because basically the nearest 0 is any of the ones that are above, to the left, to the bottom, or the right of it, right? Any of these are the closest ones, which are all 1 step away. So this is a 1 because the nearest 0 is 1 step away from this coordinate. In example 2, we're given this matrix, which I copied and pasted here, and we would return this output, which I put here as well. And basically, just like the other one, all the zeros, as we can see here, stay at 0 because the closest 0 is itself, which is 0 steps away. And then these 3 ones, sorry, this is supposed to be a 1, as we can see here. These 3 ones stay a 1 because the closest 0 to each of these is 1 step away, right? From this one, we can go up, left, or right, and that's 1 step. From this one, we can go up, and from this one, we can go up to get to the nearest 0, which is 1 step away for each of these. And this one becomes a 2 because the nearest 0 is 2 steps away, right? Because we can either go diagonal, like up and left, which is 2 steps because we have to go up and left or left and up, or we can go to this one, which will either be up and right or right and up. So that's 2 steps either way. So then this one becomes a 2. Okay, so to do this problem, we are going to want to do a BFS because this is another like shortest distance problem. And anytime we have a shortest distance graph problem, or tree or graph problem, honestly, it's usually going to be a BFS. So we can do a BFS starting from all of the zeros, actually, as like our first layer, or like our root nodes, if you will, because then we can start from the zeros and then work our way out and update the values as we go. So like all the zeros will stay a 0, and then when we hit a number that's not a 0, then we can just take the number next to it that we like got to it from as its neighbor. So like this would be a 0 plus 1 to it, and then this becomes a 1 because it's like 1 step away from it, right? And then this one we'll take the number that is, because like we'll update it as we go, and it will, so we'll get here from one of its neighbors, and so we can take the value of its neighbors, which will be all a 1 because these ones will have already been updated before we got here, and then we can add 1 to it, and then this will become a 2. So that's how we get 2 here. And then we can mark all of the 1s by updating its value to a negative number. So you can just use like -1 or something, and then the negative will just signify that it has not been visited yet. Because otherwise, if we leave it as a 1, it's going to get really confusing if we mean like it's a actual like 1 is the value, or if it's like 1 step away from the nearest 0. So by using a negative, we can sort of be able to tell easier. So I'm going to do it like that, and then we are going to just want to set up our queue for our BFS then. So I'm going to store an int array because we're going to store the coordinates of each cell. So that's going to be what we put in our queue as our nodes. So, okay, and then I'm just going to go through and loop through our matrix and add all of the zeros into the queue. And then if we encounter a 1, then I'm going to update the value to -1. So for row is 0, row is less than length, row plus plus. Okay, and then if the current coordinate is 0, we will add it to the queue, the coordinates, okay, and then if it's not 0, then it must be a 1, so we'll set that cell to a -1. So basically when we go through the entire thing, our new matrix will look something like this. And then our queue, I'll put it down here because we're going to reference it later and I don't want it to get lost. So it's going to store 0, 0. Basically all the coordinates that have a 0 in it. And then I'm going to go in order of row to column. So 0, 1, 0, 2, 1, 0, and 1, 2, right? And so that's going to be our queue, and this is going to be our grid once we're done with this loop. So once we have that, then we can actually do our BFS. But first I'm going to just set up a directions array so that we can more easily visit all the neighbors of each of these coordinates. So directions, and then again, so just the first one is going to be the representing the row, and the second one is representing the column. So a +1 means that for the row means that we're moving down, because that means we're basically adding 1 to whatever current row coordinate we're at. So if we're at 0, then if we +1, then that brings us to row 1. So that's going to be down here in this row. And then the column is 0, so the column is not moving. So if we're at like 0, 0, and then we +1, then we're moving down here basically. So +1 for row, it means moving down, which I know is confusing, but bear with me. Then, okay, so these are our 4 directions. And then again, so -1 for the row means we're moving up because the number's getting smaller. +1 for the column means we're moving to the right because the number's getting bigger. And then -1 for the column means we're moving left because this number's getting smaller. So just keep that in mind. Okay, so now that we have our directions, we can actually do our BFS. So while our queue is not empty, then we still have more BFS to do. So we're going to assign the current cell to the top node on the queue, and we're going to remove that node. So first, initially that's going to be coordinates 0, 0, so this will get taken off. Then we will loop through each direction, oh sorry, wrong one, each direction to visit all of the neighbors of this cell. So for each direction in directions, okay, and then I'm going to assign new row to, so basically we're going to take the current row, because remember in our cell, the first one is the row. So this is index 0, and this is index 1, which is the column. So we're going to take the row 1, the current row, and add that to our direction at index 0 because that's the row. So we're going to remember, because like if we start at 0, 0 and then we +1 for the row, then we're moving down to here. And that's going to be the next node that we are visiting basically. So we're going to do the same thing for the new column, so except it's going to be at 1. Okay, and then we are going to want to check that this new cell that we just created with this new row and new column is actually within bounds of our grid. So basically what that means is it has to be greater than or equal to 0 and less than or equal to the length of either like matrix.length for the row or matrix at row dot length for the column. Or you could just say like at 0, which might be easier. But if new row is greater than or equal to 0 and less than length, and new column is greater than or equal to 0 and sorry, this should be new row, that's a typo, less than at 0 dot length. And lastly, we do need to check that the value at this new coordinate is actually equal to -1. Because remember, if it's a 0, then we actually don't do anything. And if it's a -1, then that's when we actually need to update this value. So if that's a -1, then we will want to update the value. So this new cell will equal the original cells, or no, not the original, like the original as in like its neighbor that we got to it from, that cell's value. So cell at 0, cell at 1, because this is basically the row and column of the original cell that we got to it from, and we're going to add 1 to it. So basically what that means is if we originally were at this one, and then we're visiting the cell to the right, so let's say direction was, I guess the column would be increasing, the row would not be, so it would be this one. Then we're going to, like, and let's say the current cell is 1, 0, right? So from 1, 0, if we add 1 and 0, that's 1, and then 0 and 1 is 1. So then we're at 1, 1. Okay, that's our new coordinate, and this is our old coordinate. Then at our new coordinate, since it equals -1, we are taking the original coordinate, which is cell at 0, cell at 1, because that cell was our original one, right? And we're adding 1 to it. So we're taking this value, which is 0, plus 1 to it, which is 1, and this becomes a 1. So that's how that works, okay? And then once we do that, then we are also going to need to add this new coordinate to our queue. And I'll explain why in a second. So because we need to add this cell to the queue, because just in case, like for like in the case of like when we get to this one, right, then we're going to have to get to it from this one. And so to do that, we would need to have this one in the queue. So we're going to need to add that to the queue. And then once we do that for the entire grid, then we'll just return this new matrix. So when we go through, right, we're basically going to take this value, like let's say we get to this value from this 0, and it's always going to be from the shortest distance, because that's just how BFS works, okay, because we're starting from all the zeros first. Okay, so basically we'll hit this one first, we'll get down to here, and then we're going to take this value, which is 0 plus 1 to it, and then update this to 1. And then we're going to get to this one from this 0, and then we're going to take this 0, add 1 to it, and then this becomes, which is 1, and then this becomes a 1. So that's how that works. And then once we have explored all of the first layer of stuff that is not a 0, then we will finally get to this one. And so we can get to this one from either of these 3. It doesn't really matter because the result's the same. And then when we get to here, then we'll take one of its neighbors, whichever one we got to it from. Let's say it's from the left, for example. Then we'll add 1 to this value, so 1 plus 1 is 2, and then this will become a 2. And that's our final result, which is what we would return. So let's check that. Submit. All right. So in this case, our time complexity, let's think about what we're doing here, right? So initially in this loop, we are iterating through the entire matrix, every cell in here, to check if each value is a 0 or a 1. And if it's 0, we add it to the queue. If it's 1, we change it to -1. So here we're already visiting every single node once in the grid, which is m times n, where n is going to be the number of rows and n is the number of columns in the matrix. And then here we are doing our BFS, where we are basically visiting and processing every single cell again, because we're starting from all of the zeros and then like working our way layer by layer, but ultimately we are still visiting every node once more again. So that's still O of n times n. So O of m times n plus m times n still simplifies to m times n. So that's going to be our final runtime. Okay, and then our space complexity. So if we think about this one, then we have our queue, which, so if we think about this, worst case, right, because our queue we're using in our BFS. So if we think about how our BFS works, worst case, right, every single cell is going to be a 0. And if that's the case, then initially, right, none of these will be set to -1, and instead every single cell will be added to the queue at once, which would be O of m times n. So that's worst case for our queue. And then our only other data structure really is this 2D array directions, but wait, this is constant because it's only storing for coordinates in here, so that doesn't really matter. So our space complexity is also O of m times n, and it's the same variables. So that is it for this problem. Thank you guys for watching, and like and subscribe if you found it helpful. Bye!